Hi there, welcome to this second in our short videos on the 2391 scenario-based questions that you might get towards the end of your exam. You will need your BS 7671, your guidance note 3 and your on-site guide for these calculations. Remember, as you're running through, pause the video where required so that you can attempt the questions as we run through. So, this, as I said, this is the second in these short videos. So you see here, we've got that same circuit schedule that we had previously. Again, ZS at dB, 0.17. We've got the circuit descriptions, the types of wiring, reference method, number of points served, size of our live and protective conductors, and the circuit lengths, and for rings, the ring loop lengths, as well as information on the overcurrent protective devices and the maximum ZS's that are permitted for each one of the circuits. Okay. So, question we've got here is, what is the expected R1 value for the house ring circuit? As soon as I see a ring continuity type question come up, the first thing I do is I create my wee table, little r1, little rn, little r2, pop in my r1 plus rn divided by 4, leave the blanks, and same for my r1 plus r2 divided by 4, leave the blanks, so that I can then plug my numbers in once I've made these initial calculations. Okay, so we're looking at the little r1, so we're going to look at the live conductor cross-sectional area and the loop length. Remember the ring loop length, so it's 82 meters on the loop. In your on-site guide, Appendix I, or your Guidance Note 3, Appendix B, you'll find that first table in those appendices where you have your line, well, it says your line conductor and your protective conductor, but it's effectively conductor 1 and conductor 2. We're looking at the 2.5 millimeter squared conductor for our live conductors. And it gives us a milliohm per meter value at 20 degrees C of 7.41. So we take that 7.41 milliohms per meter and that loop length that we got from the circuit schedule, and we plug it into our basic calculation where we take our milliohm per meter value times the loop length and divide it by 1,000. Why are we dividing it by 1,000? Well, this is in milliohms. We're wanting an answer in ohms, so we're going to correct this 7.41. So 7.41 times 82 divided by 1,000 gives us a loop length, or a loop length, individual loop length for the line conductor, little r1, of 0.61 ohms. Follow-up question might be, what's the expected Rn value for the house? So if R1 and Rn are the same cross-sectional area, then the Rn is going to be the same value. Okay. Follow-up question from that, what is the expected little r2 value for the house ring circuit? So again, we're looking at this house ring final socket circuit, but this time we're looking down the CPC column. It's a 1.5 millimeter squared CPC. There's the ring loop length, 82 meters. Back again into the on-site guide, Appendix I, or Guidance Note 3, Appendix B, looking at the single conductor, 1.5 millimeter squared. We have 12.1 milliohms per meter at 20 degrees C. So we take those values and again we just plug them into the same calculation. This time we're looking for the little r2 value. So 12.1 times the 82 meters divided by 1,000 gives us an expected little r2, that's end-to-end loop, of 0.99 ohms. Follow-up question from that, we'd be looking at what's the expected R1 plus Rn value for the house ring circuit, and probably at the back of that you'll be looking for an R1 plus R2 value for the house ring. So that's for the stage 2 on the ring and the stage 3 on the ring expected test result values. So as I said, as soon as I see a ring continuity type question, the first thing I'm doing is whether I'm physically doing it in the real world, as you say, or doing it as a desk study. First thing I'm doing is I'm creating a wee table like this just so that I can plug my numbers in as I go. So for that first question that we just had on the previous slide, R1 plus Rn, we're going to take the R1 value and the Rn value, plug them into our calculation here. 0.61 plus 0.61 divided by 4 gives us an expected result of 0.3, and in the real world 0.3 to 0.35 if we're factoring in some contact resistance through the switch and the socket outlet. Okay, and then for stage 3, we were looking for the R1 plus R2 value. We take that same R1 value, that's 0.61, and we take the R2 value, 0.99, plug it into the calculation, divide it by 4. We're expecting a result of 0.4, and in the real world, the 0.4 to 0.45 again through the switch. Okay. So from that, what's the expected ZS for this circuit? At the top of the circuit schedule, or the schedule of test results, sorry, we have got a ZS at the dB of 0.17. So we carry out a straightforward earth fault loop impedance calculation. We take that ZS at dB and we plug that into our normal earth fault loop calc, and we're R1, R2, again, plug that into the earth fault loop impedance calculation. Remember, this ZS at dB is in place of your ZE value. So we have 0.17 plus 0.4 gives us a ZS for the circuit of 0.57 ohms. So follow-up question, does this ZS value meet the requirements for ADS? Well, in the circuit schedule, we have a house ring of 1.37 ohms. We take that 1.37 ohms, we need to remember that's at 70 degrees C. Okay, from BS7671, that's the cable's fully loaded. So we need to carry out this calculation where we are correcting it for temperature, and that's taking it from 70 degrees C down to 20 degrees C. So copper has a positive temperature coefficient of 0.004 ohms per ohm per degree C at 20 degrees. So if we take that 70 degrees C, bring it down to 20 degrees C, that's a 50 degrees C change. So if we take that 50 degrees and multiply it by 0.004, that then gives us a factor of 0.2. So we take that 0.2 away from the original value at 70, which then means that we're multiplying it by 0.8. Okay. If it was a factor of 1, sorry, if it was a factor of 1. So we take that 1.37 ohms and multiply it by the 0.8 correction factor. Yeah, okay, so that's that correction factor of 1, bring it down to 20 degrees C. So 1 minus 0.2 gives us that 0.8. So that gives us a max measured value of 1.1 ohms. Now our expected ZS is 0.33 ohms. So quite clearly that passes because it is far smaller than the 1.1 ohms that we can expect as our maximum measured. So beyond that, we then have another question where it's what's the expected volt drop on the house ring if the maximum demand on the circuit is 20 amperes. So this would be probably at the midpoint of the circuit, worst case scenario. So our R1 plus Rn value for that circuit was 0.3 of an ohm. So that 0.3 of an ohm was at 20 degrees C. So what we need to do is we need to increase that cable under full load conditions up to 70 degrees C. Okay, so what we do is we take that 0.3 and we apply a correction factor of 0.004 ohms per ohm per degree C from the cable's resistance at 20 degrees and bring it up to 70 degrees. So that's a 50 degree increase. So this time rather than multiplying it by 0.8, taking that 0.2 off of the 1 factor that we would normally apply, we then take, because our cables are measured at 80% of their 70 degree C temp, we apply a factor of 1.2 to them. So we take that 0.3 of an ohm and multiply it by 1.2 to bring it up to 70 degrees C. So we now have an R1 plus Rn value at 70 degrees C of 0.36 of an ohm. Now remember, this is not a final answer. This is just a step towards our resultant answer. So for the volt drop, we take that R1 plus Rn value that we've corrected to 70 degrees C and the design current, that 20 amperes. So 0.36 times 20 amperes, and that gives us a volt drop of 7.2 volts. Follow-up question: does this meet the maximum allowed volt drop for this circuit? Well, the maximum volt drop for this circuit is 5% of U0, the nominal voltage to earth. So 230 volts times 0.05 is how we find that 5%. That gives us 11.5 volts as a max. Now our expected volt drop is 7.2 volts. So therefore this passes as it's less than that 11.5 volts. Where did I get the 5% from? Well, it's not a lighting circuit. So we usually leave 5% for power circuits. Lighting circuits, unless it's a extra low voltage lighting circuit, all have a 3% volt drop. Okay, so hopefully that should help you in your batches of final questions that you might get for your online exam. Remember, you have plenty of examples in your handouts. The Kahoots that I've given you away, they've got plenty of examples of this in them, as well as the calculations refresher handout that's there as well. So if you make sure you're up to speed with the basics, you should hopefully not have any problems with any of these calculations in your online exam. Okay, folks, so onwards and upwards.